Now let's say, for example, that I want you to develop a Slater determinant for lithium or some other larger atom, which I will on the homework that I'm about to assign. We could set that up and say that the wave function, the total wave function for a particular atom that has a certain number of electrons, however many they are, is 1 over n factorial times the determinant of a matrix that's made of putting each electron into a particular orbital. We'll call that orbital number 1 with alpha spin, and then we have orbital number 1 with beta spin, and we put each electron, so there's electron 1, electron 2, electron 3, and so on. And that works its way all the way out to electron 1, 2, and so on being placed in the last needed orbital, with beta as the spin if it's an even number of electrons, or alpha as the spin if it's an odd number of electrons. M here is 1/2 of n if n is even, and it's 1/2 of n plus 1 if n is odd. And this works for constructing antisymmetric wave functions, because the value of the determinant of any matrix changes sign when two rows are interchanged. So I could ask you to make this for lithium, and you would have electrons 1, 2, and 3, electrons 1, 2, and 3. You would have 1s here, here, and here, alpha. You would have 1s here, here, and here, beta. And then you would have, hopefully, 2s here, here, and here, alpha. And then you would have to work out the determinant. And we're going to talk about how that's done a little bit, and I'm going to give you some resources that you can go to find places to work on that. It's also worthy to mention the value of any determinant is 0 if any two rows or any two columns are identical. So for example, as I mentioned earlier, if this were for lithium and we had 1s alpha in this column, 1s beta in this column, and then we tried to go back and do 1s alpha again for the third electron so that we could put them all in the 1s orbital, then these two columns would be identical and the wave function would collapse to 0. When we work out the determinant, we would get 0. And we'll practice that a little bit on this next slide. I want you to try to work this out on your own. Here's 3 possible, you can pause the video and write these matrices down, 3 numerical matrices to work out the determinant for. And the rules for larger than 2 by 2 matrices are fairly simple. It's going to be a series of, first of all, you're only going to make a determinant for a matrix that is n by n, that has the same number of rows as columns. But if we want to know the determinant of this matrix, it's going to be this times the determinant of these 4 minus this times the determinant of this and this plus this times the determinant of these 4. And if you need help with that, there is a pretty good tutorial at www.mathsisfun.com. I copy and pasted the address for the tutorial into the notes on this section. So if you look at the PDF for Chapter 10, Slide 9, you'll see it. And I'm going to put something similar on the homework. But just to give you a hint, once you work this out, if you work this out correctly, the answer to this one is -3. And I want you to work these out to prove to ourselves that the statements that we made earlier are true. But look at this second matrix. It's just the first one with 2 rows exchanged. We already said that if that happens, exchange 2 rows, it just changes the sign of the thing. So if this one's -3, this one must be +3. And this has 2 identical rows. So if you work this one out, you'll notice that it has a determinant of 0. So using these kinds of matrices, but putting wave functions, orbital functions, in where the numbers are gives us anti-symmetry for the wave function as well as indistinguishability. Alright, so let's look at the lithium atom illustration that I'm going to assign later on. I want you to start with this matrix. So lithium has 3 electrons. So the normalization factor, assuming that these are all normalized wave functions, the normalization factor is going to be 1 over the square root of 3 factorial. 3 factorial is 6, so it's 1 over 6 factorial. And then, again, this is incorrect. If I'm going to do 1s alpha, 1s beta, and then I do 1s alpha, the first and third columns are identical to one another, and the determinant and the wave function would be 0. But if we change this column to 2s, we'll get a work-outable determinant, and that's going to be one of your homework assignments. The other homework assignment is going to be to look back at slide number 2, the first non-title slide of this talk. Look back at the helium Hamiltonian and write out a Hamiltonian of that type that would be appropriate for lithium. So more terms, a little bit of changes to some of the numbers. These are just first approximations. The Slater determinant is going to be a first approximation for a wave function for lithium. The Hamiltonian that we write out is going to be a first approximation of a wave function for Hamiltonian. The many electron Hamiltonian can be formulated exactly, but the wave function can't. This is using those hydrogen-like orbitals with zetas in them is an approximation, and we don't know what the zeta is. That's one of the things that we need to figure out. The variational theorem states that no matter what approximate value we use for the wave function, the calculated energy will always be greater than or equal to the real energy. And this is stating that mathematically here. What that means is if we make a guess as to what the zetas are, the effective nuclear charges are, and that charge is wrong, we're going to get a wrong energy. But we're going to get too large of a wrong energy. So then we can try a different number for zeta and see if the energy gets worse. If it does, then we try a different number in the other direction. And we just keep trying different numbers for zeta and fine-tuning it until we get to the lowest possible energy that we can. And that's the way that we optimize the wave function. And so we refer to that as an iterative method. We're not able to solve it analytically. We're not able to solve it with just doing algebra. So we guess and guess and guess and fine-tune our guesses until we've made the best guess. And that's an iterative method of solving an equation. When you're doing it, making this assumption that the energy will get lower the closer you get to the real wave function, then that's referred to as a variational method. And one of the variational methods that Gaussian uses when it's solving wave functions is referred to as the Hartree-Fock SCF method. We use density functional theory, which uses Hartree-Fock method, but with a better guess at the correlation energy than Hartree-Fock makes. In order to solve for the approximate wave function of a multi-electron system, the wave function is first approximated with a Slater determinant of hydrogen-like orbitals. The Hamiltonian is approximated as a Fock operator, and the Fock operator is used to variationally optimize the wave function. The J and K, let's move my head out of the way up to, I'm going to block the title a little bit here, but you've seen that already. The J and K approximate the effective term that we talked about in the hydrogen atom with an electron-electron average repulsion operator and an electron exchange operator. And you don't need to know the form of those right now because we're not going to work out the mathematics. We're just talking about from a qualitative standpoint what the computer is doing in those cases. What we do is we operate with the Fock operator on the approximate wave function, and then we make a guess as to how we might change the wave function. If the energy gets a little better, then we use that new wave function and its new zetas, effective nuclear charges, to optimize the Fock operator. And then we use that new operator to optimize the wave function, and so on and so on and so on, until we've gotten them so close to the best that they can be, until the energy is no longer changing, until we find the lowest energy that we can find. And at that point we can use that wave function and that operator to calculate any properties that we'd be interested in for that system. And that's what Gaussian is doing when you're using Gaussian to solve an equation. It might be using, when we do density functional theory, we use better operators for J and K. I don't want to say better, but different, that get us better results. And so I'll let you look over. I won't read it to you or spend much time going over it. You can pause this if you want. But all this flowchart does is put into picture form exactly what we were just talking about on the previous slide. Assumptions that are made when we get into molecules, we'll talk about this in much more detail in chapters 12 and 13. The Born-Oppenheimer approximation is assumed. What that means is that we're assuming we can separate electron motion from nuclear motion and treat them in separate steps. Usually relativity will be ignored. We'll talk about when we can't ignore relativity again in chapters 12 and 13. And at this point we're still ignoring electron correlation. Slater type hydrogen orbitals that we've used in the past provide a good starting point for these calculations. And so those have a form that looks like this. But Gaussian functions, main difference is that the exponent depends on r squared rather than r. Gaussian functions cost you a couple percent in accuracy, so you would think, well, maybe I don't want to use those. The issue is that even though they cost a couple percent of accuracy, they make the calculation about 100,000 times faster, so it's worth sacrificing the accuracy. So those orbitals that have a Gaussian shape instead of a hydrogen-like Slater-type orbital shape are what Gaussian and other programs similar to it usually use. In multi-electron systems, energy, either way that we do these calculations, depends on N and L rather than just N. So the reason for that is that the expectation value of the radius for an electron in an elongated orbital will be higher than for a spherical orbital. That means more of the average smear of the other electrons is getting in the way. And so for those electrons, they have a decreased zeta, a decreased effective nuclear charge. And so that's why we see the Aufbau orderings that we learned in Gen Chem, the periodic table, 1s, and then 2s, and then 2p, and then 3s, and then 3p, but then 4s, and then 3d. Sorry about the phone keeps going off. I'll check that in a moment. So this might work out for an essay question. Hartree-Fock can be used to calculate the radius of an atom by finding the volume that contains 90% of the orbital density. The energy of the highest occupied orbital gives us the ionization energy for that atom. So we can determine ionization energy experimentally and then see if that energy matches what we calculate the energy of the highest orbital to be. And if it does, we know that we're, at least we have a sense that we're on the right track with our method. The energy of the lowest unoccupied orbital tells us the electron affinity. So again, experimentally measurable items that we can calculate using quantum mechanics. And the combination of these two numbers are used to calculate electronegativities. And that runs us about out of time.